You are listening to The Vocal Technologist. Spoken tech for your ears.
I am just going to call it right up front. The traditional role of tuning machine learning models, it is completely dead.
Yeah, look, the focus of engineering effort has just entirely moved on from that phase. We spent years obsessing over adjusting hyperparameters, squeezing an extra fraction of a percent of accuracy out of a single isolated model.
Right. And looking at the trajectory of enterprise architecture, that entire workflow is being abstracted away by foundation models.
Which is a massive transition for the industry.
It really is. Looking at the massive stack of research papers, architecture diagrams, and engineering postmortems we are unpacking, we're going to explore exactly what happens when AI agents take over the heavy lifting of data analysis.
Because the underlying plumbing has to completely change, yeah.
Spot on. We're going to pull apart why your underlying infrastructure has to completely change to support these new agent swarms, and how bizarrely simple database quirks can still bring this whole futuristic system crashing down.
It is wild how often the simple things break the complex systems.
Oh, absolutely. You, sitting right there listening, you are probably trying to figure out how to navigate all this without losing your mind. As your resident vocal technologist, I want to save you from drowning in endless documentation. We're just going to get straight into the good stuff.
The core issue we really need to examine is that the bottleneck for information flow has fundamentally relocated. The constraints that define data architecture for the last decade simply do not apply anymore.
Speaking of which, if model tuning is dead, what are data scientists actually doing all day? Because for ages, being a data scientist was like being an artisanal blacksmith.
That is a great way to put it.
You would take this raw, clunky data, heat it up in a Jupyter notebook, and manually hammer out these bespoke features to fit one specific model. It took forever, and the result was one highly specialized custom-built tool.
Yeah, it was incredibly manual. But moving into this new era, the data scientist is more like an air traffic controller managing a fully automated factory.
Right, you are not hammering the metal yourself anymore.
Exactly. The shift up the value chain is where the real work is happening. Because that phase of manual iteration is handled by the models, human operators are pivoting to the meta layer.
So they're looking at the bigger picture.
Precisely. They are defining the core business problems that actually need solving. They are designing complex evaluation frameworks to mathematically measure whether an AI agent is successful.
Which is a totally different skill set.
Entirely. They are curating extremely high-quality data sets, and they are building reliable multi-agent systems governed by robust human oversight. The foundational models do the grunt work, but the humans build the factory.
Right, because large language models are now entirely capable of generating highly accurate SQL queries on the fly.
Oh, absolutely. They do it in seconds.
And they're automating complex ETL pipelines, which is just the plumbing work of extracting data from one place, transforming it, and loading it into another.
Yeah, the tedious stuff nobody actually wants to do.
Yeah, exactly. They're even creating sophisticated data visualizations that used to take a human analyst 3 hours to build in a dashboard. The models are just writing the code, running it, and spitting out the chart.
And the consequence for traditional data warehouse vendors is just immense commoditization pressure. Consider the standard enterprise workflow.
Okay.
If an AI agent is writing the SQL and executing the query behind the scenes, the specific dialect or the proprietary user interface of the data warehouse matters far less.
Because the human user never actually sees the interface.
Spot on. Value shifts away from the user experience and purely towards compute efficiency and pure cost per query.
So the expensive, flashy data warehouse just becomes a silent engine humming in the background. If you're a buyer, you stop caring about the branding and only care about the horsepower.
The emerging platform architecture reflects that. It is no longer just a static repository where analysts log in to write queries manually.
It is evolving into something else.
It is evolving into an active agent swarm for data management, backed by a query engine powering the analytics.
And when you remove manual human query writing from the equation, the bottleneck shifts entirely from human typing speed to system orchestration. Just how fast can the system coordinate the agent?
Exactly.
Let us pull apart that idea of an agent swarm, because this is where reality usually hits a brick wall.
It does, yeah.
If we have this automated factory with all these agents running around doing the work instead of human analysts, how do they actually find the right answers? We have all seen AI hallucinate completely fabricated information with total confidence.
Which is why a lot of companies just threw a vector database at the problem and assumed it would magically fix the hallucination issue.
But it does not, right?
No, not at all. Relying purely on a vector database is proving to be a highly fragile architecture for production applications. A vector database is excellent for finding semantic similarity.
Like matching keywords.
Exactly. It is essentially a mathematical vibe check, matching the intent of a keyword to a concept, but it fundamentally lacks structural awareness.
So what is the alternative?
Well, a complete production-ready AI data layer actually requires 5 distinct integrated components. You need the vector store, yes, but you also need robust metadata and filtering to narrow the search.
Okay, that is 2.
You need a graph layer to understand explicit relationships between entities. You need a caching mechanism to prevent the system from recalculating the same answer.
And the 5th one.
You absolutely must have governance and observability to track exactly what the agents are doing.
Wow. 5 components just to get an agent to read data properly. That sounds less like giving the agent a compass and more like handing it a highly detailed, interactive topographical map.
That is a great way to put it. Building that map is the central challenge of modern AI architecture, which we call context engineering.
Context engineering.
Where you cannot just dump a million corporate documents into a prompt window and expect a coherent answer from an LLM. The model will just lose the thread.
It gets overwhelmed.
Exactly. So engineers are implementing precise patterns to solve this. Progressive disclosure is a major one, where the agent is fed information gradually in sequential steps as it narrows down the problem, rather than all at once.
And what about sliding window compression? Because I keep seeing that term thrown around in these engineering postmortems.
Sliding window compression is a really clever memory management technique. Imagine an agent having a very long conversation with a database. Eventually, it hits a memory limit or a token limit.
And it just forgets everything from the start of the chat.
Right, which is useless. So instead of just forgetting the beginning of the conversation, a sliding window algorithm continuously summarizes the older context into a dense, compressed format.
Oh, wow. While keeping the most recent stuff exact.
Precisely. It keeps the most recent interactions word for word. It allows the agent to maintain the overarching narrative without overloading its operational memory.
That makes a lot of sense.
Add precise context routing to that, making sure the query goes to the exact right holon of information, and you get a highly accurate system.
I want to pause on that word, holon. It sounds incredibly philosophical for a database architecture.
It does, but a holon is just a concept describing something that is simultaneously a whole and a part of a larger system?
Like a department in a company.
Spot on. Think of a human resources department. It operates as its own complete entity with its own rules, but it is also a part of the larger corporation.
Okay, I'm with you.
In data architecture, structuring knowledge into holonic graphs creates strict boundaries. An agent operates within a specific holon, like the HR data holon.
Which physically prevents it from wandering off and hallucinating across unrelated domains like sales data.
Exactly. It keeps the system grounded.
When you get those boundaries right, the results are wild. Look at what is happening over at Grab.
Yeah, their results are genuinely impressive.
They have successfully deployed multi-agent systems to resolve up to 40% of their repetitive user queries completely autonomously. We are talking about agents navigating across over 15,000 tables of enterprise data.
Which is a massive scale.
It is huge. They are reclaiming hundreds of engineering hours every single month because the agents are doing the initial triage and data fetching.
But autonomy at that scale requires a total rethinking of validation. Moving these agentic systems into production environments is notoriously difficult because of the testing barrier.
Oh, this is the part that genuinely terrifies me.
It is a bit daunting, yeah.
The reason it is brutal is because probabilistic outputs completely break traditional deterministic testing. So, for the listener, deterministic software means 2 plus 2 always equals 4. You write a test, you check for the number 4.
Simple and predictable.
Right. Probabilistic software means 2 plus 2 might output the number 4, or the word 4, or a sentence saying the answer is 4.
Which is a nightmare to test.
We are literally building enterprise software that we cannot test with traditional rules because it just guesses differently every single time.
Which, yeah, is exactly as terrifying as it sounds.
It completely breaks the fundamental contract of software engineering. You can no longer rely on rigid string matching or basic assertions. So how do you actually test it?
This necessitates human-in-the-loop processes, but also emerging frameworks where engineers use one large language model as a judge to evaluate the output of another working model.
Wait, really?
Yeah, the judge model is prompted to test for reasoning, logical flow, and factual grounding against the source text, rather than looking for an exact character match.
So we are at the point where you hire an AI to supervise your other AI.
Exactly. You build an ecosystem of checks and balances. But to run an ecosystem of LLM judges, complex Hellenic graphs, and multi-agent triaging, the underlying plumbing of the enterprise just will not survive.
It just collapses under the weight.
Yeah, engineers are being forced to completely rewire the engine room. If you have a massive swarm of agents firing off highly complex interactive queries simultaneously, legacy batch systems are going to collapse under the concurrency load.
Because batch systems were designed for human paces. An analyst requests a quarterly report, hits enter, and goes to get a coffee while it runs in the background.
Agents do not drink coffee, and they do not wait. They fire 10,000 questions a second.
Right.
AI workloads are forcing the aggressive convergence of real-time analytics, data warehousing, and observability into single high concurrency platforms.
So you cannot just have different silos anymore.
No, the old model of keeping your data siloed across different latency tiers, where some data is fast and some is slow, it just creates unacceptable friction for an agent swarm.
And here is where it gets properly weird and amazing. Because traditional systems crash under that AI load, engineers are completely rewriting the engine room from scratch. Volga is a perfect example of this.
Volga is fascinating.
It is a real-time AI and machine learning engine that was just rewritten entirely in Rust.
Okay.
They completely ripped out the old Python and Ray core just to get maximum performance.
Rewriting a core engine in Rust is a massive undertaking, but it provides tight deterministic control over memory management and execution speed.
Which is critical for these loads.
It is critical when you're trying to unify streaming data, historical batch data, and request time compute. By running all of this in one standalone system, Volga eliminates the need for data teams to stitch together incredibly complex, fragile pipelines using a mix of Flink, Spark, and Redis.
It just strips the architecture down to its bare essentials.
Exactly. It uses Apache Data Fusion for its SQL pipelines and SlatedDB for state management.
Let's talk about that state management, because that flows perfectly into what is happening over at Tansu.io. Tansu is rethinking data streaming by creating a stateless Kafka-compatible broker.
Which is a huge shift.
It really is. Now, a traditional Kafka broker holds onto data, which means it requires massive amounts of expensive memory and constant babysitting by platform engineers. Tansu shifts the durability entirely to external storage, like S3 or Postgres.
Decoupling the storage from the broker fundamentally alters the physics of the system.
How so?
Because the Tansu broker no longer has to physically store the massive log of data itself, its memory footprint drops to roughly 20 megabytes.
Think about that. 20 megabytes. That is like moving out of a massive, incredibly expensive warehouse where you keep all your physical belongings and instead living in a tiny 20 megabyte apartment.
Because you teleport your stuff away?
Exactly.
Oh.
Because you finally figured out how to instantly teleport your belongings to cheap self-storage whenever you need them. You get all the living space, none of the clutter, and it is dirt cheap.
It is a brilliant model.
But hold on, I have to push back here. If Tansu shifts all its durability to external storage like S3, does that not create a massive latency problem for the listener trying to build a real-time application?
You would think so, yeah.
We're talking about sending data across a network to an object store. How on earth does it stay fast?
That is the exact architectural tension they had to solve. It stays fast because the Tansu broker only handles the routing and the acknowledgement in memory.
Oh, I see.
It uses an asynchronous background process to flush those validated records to S3. Because of that lightweight footprint, it enables 10 millisecond scale to 0 deployments.
Meaning it shuts down when not in use.
Spot on. The system spins up instantly when a surge of data hits, processes the routing in milliseconds, writes directly to open table formats like Iceberg, and then vanishes when the traffic stops.
Okay, but before we get too lost in the futuristic clouds of instant teleportation storage and scale to 0 deployments, we need a massive reality check.
We always do.
Because for all this advanced infrastructure, for all the Rust rewrites and Hellenic agent swarms, the biggest bottlenecks are still bizarre quirks in the fundamental databases we use every single day.
It is the ultimate irony of systems engineering. You can build the most sophisticated orchestration layer in the world, employing LLMs as judges and vector caches. but it all eventually executes on relational algebra at the bottom of the stack.
Imagine you were sitting there wondering why your cloud compute bill randomly spiked by 50 grand. You might assume you have a traffic surge,
But no, it could literally just be the Snowflake or R join trap.
which is wild. If you use a simple OR statement in your join conditions in Snowflake, it completely breaks their hash join optimization.
The mechanics behind that trap are a perfect illustration of why understanding the query engine matters. A hash join is an incredibly efficient way to combine two massive tables.
Right.
The database engine builds a dictionary, a hash map, in memory. It scans the first table, maps the keys, and then instantly matches the rows from the second table.
But the moment you introduce an OR condition, the engine cannot safely use that dictionary because the logic branches. It panics and falls back to a Cartesian product.
Which is catastrophic.
It really is. It means it multiplies every single row in Table A by every single row in Table B just to check the matches. If you have a million rows in each table, suddenly the database is trying to process a trillion combinations.
It forces massive performance slowdowns. However, the fix requires no new infrastructure.
You just change the code.
Exactly. If you rewrite that one OR statement as two separate equity joins, essentially asking two simple questions and combining the results, you restore the efficient hash execution. Engineers regularly see 100 to 200 times speedups just by changing the syntax of the question.
Imagine building an elite AI agent swarm, upgrading your entire infrastructure to Rust, tuning your Hellenic graphs, and then the whole system grinds to a total halt because a coworker used an OR statement in a Snowflake query.
It happens more than you think.
Because apparently that is where we are now. It is incredibly frustrating, but also completely hilarious.
It highlights a critical truth in data engineering. The question is the contract. Whether you are dealing with a complex multi-agent system or a simple SQL database, how you phrase the question determines the physical mechanics of the answer.
And it is not just Snowflake. Datadog ran into a wild performance issue with Postgres.
Oh, the upsert issue.
Yeah. They were cleaning up millions of ephemeral hosts, and they used a simple upsert command to update a last seen timestamp, insert the row, or update it if it already exists. Simple, right?
You would assume so.
But that single operation doubled their disk writes and quadrupled their write-ahead log syncs. For the listener, the write-ahead log is basically the database furiously writing down a secure history of changes in case it crashes.
This is a classic example of implicit database mechanics causing chaos at scale. In Postgres, the onConflict_do update command always acquires a row lock, preventing any other process from touching that data.
Crucially, it writes to the write-ahead log, even when absolutely no data has changed.
Datadog was hammering their physical disks with no upserts, locking rows and syncing logs for zero actual data mutation.
They were updating a timestamp to the exact same time, and the database was treating it like a massive operation. The fix was just adding a condition to avoid locking on no upserts, but you have to know that the lock is happening in the first place. You have to look under the hood.
You cannot treat the database as a black box. Etsy faced a similar existential threat with their routing logic.
What happened there?
They had to completely migrate their database sharding architecture to Vites. They were trying to escape a legacy MySQL setup where a single unsharded index database became a dangerous single point of failure.
Oh, I read about this. That unsharded index was acting as a central directory across over 1,000 individual tables.
Uh-huh.
If that one central directory database went down, the entire routing logic for Etsy went down with it. They migrated to Vites, specifically to abstract that sharding complexity away from the application developers and physically eliminate the single point of failure.
Which ties everything we have discussed perfectly together. Whether you are building an AI data layer with progressively disclosed context or scaling a traditional e-commerce marketplace, understanding the exact execution mechanics is the only way to survive.
The infrastructure might be getting smarter, but the fundamental laws of database physics still apply.
It keeps us humble, yeah.
It really does. We are building systems that can autonomously resolve complex business logic across 15,000 tables, but we still have to babysit the row locks and the join conditions.
We certainly do.
Well, look, if giants like Azure and OpenAI are maxing out the world's GPU supply just to run these intensive architectures, causing a $625 billion backlog, you need to seriously rethink your own compute backup plans. If the big clouds cannot even supply themselves, what does that mean for the rest of us trying to scale these new data architectures? Keep questioning your infrastructure and never trust a simple OR statement. As your resident vocal technologist, I will catch you in the next one.
Spoken Tech for your ears.